Hello, we're Group 7. My name is Mia, and my teammate Lulu, Elay, and Heyan are here, and we are introducing our Design Lab 2. This is the flashlight parts individually, as he's showing in the picture. There are 8 parts. This is our precedent diagrams and all the activities that we use for Design Lab 1. And the data collection and task time also for Design Lab 1. And this is we used rank position weight to calculate our workstation. And this is our Design Lab 1 results. And you can see option 2, before we calculate K0 as 4, however, we think that using 5 workstation would be a better option. And this is our workstation design flow. And we use this for workstation display. And this is our assembly line execution. So with 12 cycles, 5 workstations, the expected production was 7. We actually produced 8 units, and at 4:14, our workstation 1 was empty already, and we had buffers at workstation 1 and 5. So we ran through the assembly lines 30 times to get an average workstation time for each workstation. And it turns out that the actual workstation time was a lot higher than the one we predicted. So this assembly line has issue. We have to come up with a new design. So this is a list of the problems we have with the original assembly line. So before we discuss about our problems and solutions, we first look into the metric development. So our goal for the quality of our assembly line is safety, quality, productivity, and reliability. And we focus on those 4 points based on Lean Six Sigma. And here are some of the metrics from Lean Six Sigma and their definitions. So for productivity, Lean Six Sigma introduced labor productivity and total people productivity, which is units produced by divided by labor hours. And quality will look into first pass yield, which is percentage of units that meets requirements, and defects, which means that the ones that didn't work. And total productivity maintains just mean time between failure and the machine uptime. So this is just an example of our metric. The table on the left is showing categories criteria, which we discussed before. And so for before design and after design, there will be 2 different numbers. And for this metric, what we do is that we would calculate those numbers, and then we'll compare the two numbers and give a score to it. So if you look at the table on the right, you see there's +1 and -1. And for +1 would be if, for example, for productivity, after design will give, if its productivity for after design is higher than the before design, then we'll give a +1 to the after design and a -1 to the before design. And a total number decide which option would be a better option.
For workstation 1, there are 3 tasks performed, and you can see task C takes the longest time to finish. So we find the problem is the silver case and LED lights are not symmetrical, so that workers cannot attach these 2 materials together. As you can see from the video, the silver case has to be exactly at the right position to attach to LED light. Our design is trying to achieve a simple attachment of LED light and silver case so that they can match to each other at any position. As a result, we designed 2 different symmetrical layouts for LED lights. Compare these 2 designs. The upper one is easier to accumulate heat, which may cause breakdowns of LED lights. Finally, we determine the LED light and the silver case layout design as shown on the screen. And here is the ideal revised workstation video, which is much faster than the old design. We also run through the tasks 30 times to assure to have a reliable result. The average task time is reduced from 5.56 to 2.72.
In our workstation 2, there has two tasks in it, which is task D and task G. And the problem of workstation 2 is about the installation of LED box. The wire from LED board easily breaks while inserting the battery box to front case, resulting in faulty flashlights. The video shows the actual situation when we insert LED box into the front case. There is only one way to match the LED box to the front case, so we should find the right position of LED with silver cover on. And also we see the wires are interrupting us when we insert LED box, and the wires are easily broken. In our workstation 2, so we based on the design of manufacturing principle, so we want to shorten the wires in order to prevent the wires broken. So we use the glue gun to glue the LED light with the battery box. The video demonstrates our new design can easily to put the battery box into the front case. The slide shows our 30 sample data. The average test time reduced from 15.79 to 6.96. In our workstation 3 and 4, there has two tasks, which is E and F. The problem from our workstation 3 and 4 is the screws were too small and hard to handle it, and also the restricted access for assembly screws. As we can see, it's hard to insert 4 small screws to LED box because the screws can easily hang up or fall outside of the hole. According to the design principle of manufacturing design, we want to part located before release. And the second principle is to introduce a very small thing in hard to pick up. So our solution for our workstation 3 and 4 is increasing the tail length of screws and also increase the head size of the screws for easier pickup. We use the SolidWorks to demonstrate our new design. The picture on the left is our original design. In order to insert the battery box into the front case, we have to reach in with hands. By raising the platform, we can eliminate the issue. Also, the screw can be easily fastened with this method. Here is our revised design model. Here is also our 30 sample data, which shows the time reduction from the old design to our new design.
Workstation 5 is to use 2 screws to secure back case into front case. It took too long. So this demonstrates originally how we put the back case into front case. So we adopted ideas how to twist the cap for the water bottle and other flashlights. As we can see from table, we required around 20 seconds to finish this workstation when we use 2 screws to secure back case into front case, but after the design we only need about 8 seconds. This video demonstrates how we ideally twisted back case into the front case. As for the battery problem, the primary parameters which causes battery quality problems are temperature, time, humidity during transportations and storage. High temperatures and humidity cause internal reactions to occur which leads to batteries leaking problem, and many batteries will lose capacity more rapidly. As for the battery solution, we use Poco Yaki from Six Sigma. Its purpose to eliminate product defects by preventing and correcting. Proper storage and transportation extends the life of the batteries and prevents them from becoming a safety hazard. The first step is keep batteries in the original packaging if possible before they come to assembly line. And the second one is store batteries according to different order times, so we would always use the batteries has the earliest order time. Third one is store the batteries in suitable temperature between 5 to 15 Celsius degree and 25% relative humidity, or store them in vapor-proof container to extend battery's life. The fourth one is in order to prevent electrical conduction, instead of store them with other metal, we decide to store them in plastic shelf. And the last one is batteries will quickly discharge when they install in a device, so we restricted the amount of batteries ordered to be the same as customer demand. And for the purpose of quality management, in order to ensure customer satisfaction, although increasing the expense on preventing, it can decrease sample test fee and benefit on company's reputation. We set an inspector before the assembly line in order to make sure all batteries work before they go into the assembly line. As for other improvements we consider tool using, we decided to change our tool screwdriver into power screwdriver according to the ergonomics principle, which is in tool using, which is bending the tool not wrist, and when manual hand tools are used for tasks that require the frequent and repetitive use of force to perform a task, the risk of contracting and work-related musculoskeletal disorders increases. Well, if our workers are injured, we need to pay for the treatment of injury and will cause a pause of assembly line, which will lead to a failure to meet the customer's demand. Additionally, maybe we even need to re-employ new workers, which will increase the labor cost. Consider we have 3 workstations to screw up screws, which are repetitive tasks. We decided to use power tools instead of hand tools. And also we decided to use a glue gun to stick the LED light and LED box together.
So let's conclude of our new design. So we made a few changes, and the task time according to those changes has significantly reduced. So we had to calculate a new K-naught, which turns out to be 4 workstations. Therefore, we changed our 5 workstations into 4 workstations. And this is our new pre-descending diagram. Since we changed 5 workstations to 4 workstations, the activities also had to reduce. And this is our new workstation display. And also, we ran through the new design assembly line 30 times, and we came out with the average workstation time for each workstation. The number reduced a lot compared with the old workstation design. So now let's look at metric comparisons. So we look at the table on the left. If we look at productivity, quality, and total productivity maintains, we calculate 2 different numbers. And if you look at productivity, after design has a higher productivity than the before design. However, the reason why we gave both 2 designs a +1 for that productivity is because both of the design meet the requirements, which is 5,000 units per week. So we think the productivity is already enough. However, if you look at quality, before design it's much lower than the after design. So we decided to give after design a +1 and then before design a -1. And also we gave after design a +1 on the safety, because now we have battery, transportation, storage safety that wasn't mentioned for the before design. So if you look at total numbers, now after design has a +6 and before design has a -2. So our after design, which is the new design, is the optimal solution for our design. So let's look at our budget. So let's assume for the old design, we will use the old design for year 1 and then use the new design for the year 2. For year 1, we spend 3.72 for our part cost for each unit, and we increase that amount in second year based on a more difficult producing parts, or more screws or less screws, so that increased. However, the price we're selling it stays the same since the function that did not change. Our transportation and storage and holding costs also increased with tool usings and waste cost. This waste cost is basically for the company that we hire to produce parts. Since now we can't use those parts, we're not going to use the old parts anymore. for them, it's also that they wasted that amount of money, so we had to pay for them. And also we consider as design fee, since we hired people to create new design, we also had to pay that. And now look at the profit of the second year. Even though it's much less than first year, however, it's still showing that we're still gaining some money. So we believe that if give another year try, we believe the second design would have much higher profit than the first year. So with this budget calculation, we believe our design is economically feasible. Here are some equations that we use for calculating the budget. Thank you very much.